Good afternoon. This is Math 2413. Today is November the 27th. A few announcements. First of all, to start off class today. The Exam 3 review is posted. Please be working on the review this week as you're preparing for Exam 3. The Exam 3 testing window opens November the 30th, so that's this Thursday, goes through December the 5th. I will be assigning a take-home problem for Exam 3. I gave some details on that in an email that I sent out to everybody yesterday, so be looking for that. I'll be emailing everyone the take-home problem on November the 29th, and that is due by the end of the day on December the 5th. It should be a one-page problem, so you shouldn't need more than one page, and you're just going to send that back to me, and that will be worth probably about 5 points on a problem on Exam 3. Final exam review, I'll be posting that by the end of the week, hopefully by Wednesday, but by the end of the week for sure. Also, I want to remind you that on the final exam, you will be allowed to bring in a 3-inch by 5-inch note card with any notes that you want written on it, front and back. So be thinking about what you want to write on a note card that you're going to bring with you to the final exam. The final exam window is December the 7th through the 11th, so that's next Thursday, December the 7th, and it'll run through Monday, December the 11th. I will be on campus this week on Wednesday, November the 29th from 4 to 6 p.m. and on Thursday, November the 30th from 9 to 11 a.m. Come on by if you have any questions. If you want to go over some stuff with me in person, I will be happy to help you out, whether it be for the review for Exam 3, the final exam review, homework 6, whatever. Please come on by. The key for homework 5 that you turned in, or some of you turned in last week, I'll be emailing that out later today, and the grades on Exam 5, or on homework 5 rather, will be posted by the end of the week. Homework 6 is due by the end of the day, December the 6th. That's a postponement from when I had it originally set for. Finally, your last lecture will be Wednesday, December the 6th. That's next Wednesday. So I'll be lecturing today. No lecture on Wednesday of this week. No lecture on Monday of next week. And then last lecture will be next Wednesday, December the 6th. Today we're going to be looking at integration and inverse trig functions, and then a very brief introduction to the hyperbolic functions, so that if you get into Cal 2, then your professor starts talking about the hyperbolic functions, that you have some idea of what they're talking about. All right, so let's go on and let's get started on integration and the inverse trig functions. Now that we've come out of looking at substitution, we did a lot with substitution last week, and so you've seen quite a few examples if you've been looking at these lectures on U substitution, and I can't emphasize to you enough how important U substitution is as a Cal 2 student. So as you go into Cal 2, your professor is going to expect that you can do U substitutions. So be really working on that. All right, so we are talking about integration and the inverse trig functions. That's our primary goal for the day today. Now, if you recall that we have a derivative for example, the arctangent. And we're going to start off with the arctangent function and work exclusively with the arctangent for a few minutes. But remember that the derivative of the arctangent function, the arctangent of u of x is equal to u prime divided by 1 plus u squared, or u prime of x over 1 plus u of x squared. All right, so that combines the basic form for the arctangent function along with the chain rule. So if you turn that form around and look at it as an integral form, then as an integral form, this would be du over 1 plus u squared. The antiderivative for du over 1 plus u squared would be arctan u, and then plus an arbitrary constant. We would like to make this a little bit more general. Instead of writing it as du over 1 plus u squared, we would like to write this as du over a squared plus u squared. And so we want to write out a form for du over a squared plus u squared. All right, so what I'm going to do is I'm going to derive this form from the more basic form above it. And we're going to do that right here. So, you know, the basic form has 1 plus u squared in the denominator. And so that's what we want in our integral, is we want a 1 plus a 1 plus something squared, right? And so if we start off with this form, du over a squared plus u squared, where a is some real number, and we multiply the numerator and the denominator by 1 over a squared. Now, the reason why we would do that is because that would give us that 1 as the leading term in the denominator, right? So when we do this, in the denominator, we're going to have a squared over a squared plus u squared over a squared. And in the numerator, we just have 1 over a squared du. Now that 1 over a squared du, or the 1 over a squared in the numerator, is just a constant. So that could be brought outside of the integral, which we would do. And then you have du over 1 plus a squared over a squared is 1. And then u squared over a squared we could write as u over a quantity squared, like that. All right, so now the idea is to try to match it up with our that basic form that we have written above, where you have du over 1 plus u squared equals arctan u. All right, so to make it look like that form, we're going to use a substitution. And so let's say we go to v's. We'll use v as our variable. And we let v equal u over a, or 1 over a times u. Either way you want to write it. Then dv, remember, would just be the derivative of this function. So that would just be 1 over a, because 1 over a is a constant, du. And so that would be our dv right there, 1 over a du. And so when we go up to our integral, we want to make a substitution. Well, you know, we're going to need a 1 over a du in the numerator. So what I'm going to do is I'm going to rewrite this integral down here. I have this 1 over a squared sitting in front. And then we just rewriting the integral is all I'm doing here. And you want a 1 over a du in the numerator right here. So I'm going to multiply in the numerator by 1 over a, so I can make this substitution. But if I multiply by 1 over a in the numerator, then I multiply by the reciprocal in front of the integral, and so I multiply by a in front. All right, so when I do that, in the front of the integral, the a's would cancel, and we just have 1 over a, and then this would be times the integral of, and we can make our substitution, and 1 over a du would be equal to dv, and then in the denominator I'd have 1 plus u over a, but u over a is equal to v, and we have 1 plus v squared. And now this form is the basic form right here. It matches up with the basic form exactly. And so I would get 1 over a times, and this would simply be arctan of v plus c. And then v, just simply go back to u's here. And so we would get 1 over a arctan of u over a plus c. And we've derived our form. So this form here is going to be 1 over a arctan of u over a plus c, where u represents some function of x. And so this is our basic form for the inverse tangent function right here. This is the form we will use in calculus when we're trying to find an antiderivative and it ends up being an arctangent. All right, so looking at that form, and I'm going to write it down again at the top of this page right here. This is a very common form to use or to encounter in calculus, so definitely need to be prepared for this. All right, so we put that form down and write it at the top. So now let's look at some examples and let's see how this is going to work out. So we're going to start off with some pretty straightforward examples. we have dx over 9 plus x squared as our integral right here, our indefinite integral. Now, I'm not going to formally go through and make a substitution each time. What I want you to do is try to learn how to match this form up with the basic form. And so what you're going to do is look and see if you can find u and du and a, all those little pieces of the integral. And then once you've identified properly the u, the du, and the a, then you ought to have the form. So in our problem here, does it match the form? Well, it would if u is equal to x, right? Because that's what's squared in the denominator is x. And then du would be dx. And notice I have that exact quantity in the numerator. And then a would be equal to 3, because a squared it would be equal to 9. And so this matches the form exactly. So matches form exactly. And so I should be able to just write out the antiderivative here. It would be 1 over a, so it would be 1 over 3 arctangent of u, and u is x in this case. That's the function that's squared. X over 3, and I usually try to put parentheses around that, and then plus an arbitrary constant. And you've got the antiderivative. 1/3 arctangent of x over 3 plus c. So that's a pretty straightforward example. Definitely need to be prepared for this kind of problem to just occur very frequently in a Calculus 2 class. All right, let's look at another example. We're going to look at numerous examples here, and we're going to gradually look at more complicated problems as we move along. So the next one is dx over 25 plus x squared. So we look at our form at the top, and we see if we can match it up with the form. Right? So in the denominator, always the first thing to focus on is what's u? What is the function that's being squared in the denominator? Remember, that would be u squared right there. And so our function is going to be x. U is equal to x. And then du would be dx, just differentiating there. So that all matches up perfectly. And a would be 5, because a squared is equal to 25. So this matches the form exactly. And so we can write out the antiderivative. It would be 1 over a, 1 over 5, arctangent of u over a, so that would be x over 5 plus c. Like that. So we have 1/5 arctangent of x over 5 plus c would be our antiderivative. All right, so far very straightforward. All right, let's go on to another problem. So a little bit different now in the next problem. On this next one we have in the numerator 2x dx, and in the denominator we have 1 plus x to the 4th. And you also will see this integral written like this as 2x over 1 plus x to the 4th dx. You'll see that written interchangeably like that. All right, so the thing to focus on first of all is what function is being squared in the denominator. And if you look at that, this problem, in the denominator, instead of 1 plus x to the 4th, we could write this as 1 plus x squared squared, like that. Right? You want to identify what function is being squared in the denominator, because you're trying to match it up with the arctangent form, and the arctangent form is a squared plus u squared. And remember, u is some function of x. So in our problem, what would u be equal to? Well, u would be equal to x squared, because that's the function that's being squared in the denominator. And then du is equal to 2x dx. And notice that's exactly the form we have in the numerator. So it matches perfectly. So that's great. And then finally, a would be equal to 1, because this is a squared plus u squared, but a squared would be equal to 1 here. And so we are ready. This matches up exactly with the form that we've written at the top. So this is going to be 1 over a. So this is going to be 1 over 1 arctangent of u over a, which would be x squared over 1 plus c. And so we end up with arctangent of x squared plus an arbitrary constant. And there's our antiderivative. Okay, so that problem, again, pretty straightforward, but you did have a little bit different kind of function that was being squared in the denominator. Please take the time to write down what u is, what du is. Make sure those are both exactly in the integral like you need them. And then identify what a is so you can write out the basic form. All right, the next page, let's go on to the next screen. Again, let's write down our form at the top of the page. Let's keep this form in mind. Right now, we're just working with the arctangent function. We will move on to the arcsine and the arcsecant in a little while. So here's our form. All right, so our next problem. And this one we'll find it does not exactly match. And we have to do a little bit of manipulating to make this match the basic form right here. Oh, I'm sorry, not a 9 in the numerator, that's a dx in the numerator. Here we go. So you have dx over 10 plus 9x squared. You may also see this written, remember, as 1 over 10 plus 9x squared dx. You'll see it written both ways. All right, so if you look at the denominator, you want to look at what function is being squared. And in the denominator, the function that's being squared is not x, because you have a 9x squared there. Remember, you have to write that term as the square of a function. So to write it as the square of a function, we write this as 3x quantity squared, like that. You have to write it that way. You have to write it as a function squared. All right, so if we let u be equal to 3x in this problem, that's the function that's being squared in the denominator, then du would be 3dx. And so notice here in this problem, in order to make it match, we don't have a 3dx in the numerator. So in the numerator, I multiply by 3 to make it match, and then I multiply by 1/3 outside the integral. Right? Remember, you have to do the reciprocal on the outside when you're multiplying something on the inside like that. And now it matches exactly. That is now du in the numerator. All right, and then don't forget, we also have to identify what the constant a is. And the constant a in this problem would be the square root of 10. Remember, this constant represents a squared. So if a squared is equal to 10, then a would be the square root of 10. All right, then the 1/3 that we had to insert in the previous step just comes along for the ride. And then you have times 1 over a, so this would be 1 over the square root of 10, and then arctan of u over a, so that'd be 3x over the square root of 10, and then plus an arbitrary constant. All right, now to be honest with you, if you wrote it in this form, I would actually not have a problem with that. I'd be okay with this. But, you know, you should write it as 1 over 3 square root of 10 in the numerator, certainly. 1 over 3 square root of 10 is the constant outside of the arctangent here. But you will see textbooks, and you may have a professor next semester who really wants you to rationalize those denominators there. So make sure you know what your professor wants you to do here. So if you have to rationalize, you know, you're going to multiply by the square root of 10 over the square root of 10, and you're going to do the same thing here, square root of 10 and the square root of 10 to rationalize that. And so when you do that, in the numerator, you'd have square root of 10, and the denominator, you'd have 3 times 10, or 30. And then this would be arctangent of, in the numerator, I'd have 3x times the square root of 10, and the denominator, the square root of 10 times the square root of 10 is 10. And so that would be the form for the antiderivative if you had to rationalize the denominators. Pay attention to what your professor wants you to do in Cal 2. I personally would not care if you just wrote it the first way and did not rationalize it. To me, that's not too big a deal. All right, next example. This one also will look pretty different. You have the integral of e to the x over 49 plus e to the 2x. And this looks in this then dx. This would not probably initially cause you to think arctangent at all on this problem, but you do have an e to the 2x in the denominator and just an e to the x in the numerator. And so what you need to realize in this problem is that that e to the 2x in the denominator could be written as e to the x quantity squared, because you multiply exponents. And if you think of it that way, now all of a sudden it starts taking on the form for the arctangent form, right? If we let u be e to the x, because that's the function that's being squared in the denominator, then du, sure enough, is what I have in the numerator. It's e to the x dx. It's exactly what we have in the numerator. And so, in fact, this is an arctangent. It didn't look like an arctangent at all initially. Right? And then a would be equal to 7. So when you see fractions like this now, you need to start thinking about, could it be an arctangent form? All right, and so we're ready to write out the arctangent form. You have 1 over a, so that'd be 1 over 7, arctangent of u over a, but u was e to the x, and a was 7. So you'd have e to the x over 7, and then plus an arbitrary constant. And there's the antiderivative. You know, we're going through more and more different kinds of problems for integration, and so you need to just start getting more and more experience, and you really need to practice and work problems. And you know, that's one of the downsides to taking this class as an online class, is you don't have a classroom setting where somebody is telling you, hey, do these problems. And so this is kind of left up to you to work on this at home, but you need to work problems, and working the homework that I've assigned is going to be very helpful in these kinds of problems. The more practice you get just with integration in general, the better off you're going to be. All right, so let's look at another example. We are working through a lot of different situations here. So in this problem, we have dx over 5 plus 36x squared. So this problem looks very similar to something we've already done. And again, remember, you might see this integral written like this instead, as 1 over 5 plus 36x squared dx. All right, so you need to identify a function that's squared in the denominator if you are going to match this up with the arctangent. And so 36x squared you'd rewrite as 6x quantity squared. All right, and so what would we do here? We would let u, what's the function that's being squared in the denominator? Well, that's 6x, so u would be 6x, and then du would be 6 dx. I don't have a 6 dx in the numerator. I just have dx, so I multiply by 6 in the numerator and then 1/6 outside of the integral. And now this was going to match up exactly. I also identify what a is. A squared would be 5, so a would be the square root of 5. All right, so this matches up exactly for an arctangent. And so this is going to be 1 over a, so this would be 1 over the square root of 5, arctangent of u over 5, so this would be, or u over a, so this would be 6x over the square root of 5, and then plus an arbitrary constant. And again, another problem where rationalizing the denominator might be something you'd want to do. If you do that, you get square root of 5 over 5 in front of the arctangent, and then inside the arctangent you have 6x square root of 5 over 5 if you rationalize the denominator. I also want you to always kind of keep in mind, this is our form, is du over a squared plus u squared, and it must match exactly with this form in order for your antiderivative to be an arctangent. If you can't make it look exactly like this form, then it is not an arctangent. So for example, in our problem that we just did at the top of the screen, if we had dx over 5 minus 36x squared, it does not match. the arctangent form. Even though it's just a subtraction instead of an addition, this does not match the arctangent form. And so this integral, in fact, is not an arctangent. This is actually going to involve trig functions, and this is a Cal 2 problem. But if there's any deviation at all, then it doesn't fit the form, right? So you've got to make sure that it fits the form exactly. All right, the next problem I want to look at, let me write the form down again at the top of the page. So you have du over a squared plus u squared. That antiderivative would be 1 over a arctangent of u over a plus a constant. So we're going through different situations and how you make these match that form. Now this problem, the denominator certainly does not look like a squared plus u squared. It's just x squared plus 4x plus 13. It's just written out as a trinomial. But I need to write it as a square plus a square if I'm going to try to match this up with the arctangent form. And so the way to try to make this match is to complete the square in the denominator. If you complete the square in the denominator, you can make it match. So we're going to write complete the square in the denominator. So to do that, remember how we go about completing the square is we write x squared plus 4x down, and then we move the 13 over, like so, and then we complete the square in the trinomial, right? So remember, you take half of the middle coefficient and square it. So I'm going to be adding in a 4 right here inside the integral, inside the denominator of that integral. But we're not allowed to just change the integral here. You know, just adding in a 4 like that changes the integral, unless we also do the opposite and subtract 4 in the denominator also. So now in the denominator, we're adding 4 and subtracting 4. It means we're not doing anything at all. And this equal sign that I wrote at the beginning of this line is legitimate, right? That this integral is equivalent to the integral before. Because all I'm doing is, in the denominator, I'm adding 4 and subtracting 4, which means I'm really just adding 0 in the denominator. But the advantage to this is that this trinomial is always factorable, remember, and it always factors as the square of a binomial. And so you get dx over x plus 2 squared plus 9. Or, you know, if it bothers you to put the x plus 2 first and the 9 second, there's no reason why you couldn't switch the order of these two terms and write it like that. It makes no difference at all since it's an addition problem. Those are the same thing. And now all of a sudden you've got this function squared in the denominator, and so this seems to be an arctangent, right? If we let u be x plus 2, that's the function that's squared in the denominator, then du is going to just be dx, because the derivative of x plus 2 is 1. And so it's going to match exactly, isn't it, for the arctangent form. A would be 3. A squared is 9, so A would be 3. And so this is exactly an arctangent, as it turns out, after we completed the square. And so you get 1 over A arctangent of u over A, and u is x plus 2 in this case. It would be x plus 2 over 3, and then plus an arbitrary constant. Okay, remember, by the way, you can always check these and make sure that if you differentiated this function, that you got the original function back. All right, so completing the square is a way sometimes to take a trig function and or a quantity like this and make it match the arctangent form. All right, so next problem. Let's say we have dx over x squared minus 8x plus 25. So this problem, you know, now that we've done the one just before it, is looking like the very similar kind of problem. where we would want to complete the square to see what we can make the denominator look like. So you have 8x squared minus 8x. We slide the 25 over, and we take half the middle coefficient and square it. So half of 8 is 4. 4 squared is 16. So I'm going to add 16 here and then subtract 16 on the outside, like that. So this problem works exactly like the one we just did. Right, no differences here. So when we factor in the denominator, we get x minus 4 squared and then plus 9, like so. So sure enough, this matches exactly, right? If we let u be x minus 4, that's the function that's being squared in the denominator. Then du would be dx. The derivative of x minus 4 is 1. So you just get du to be 1 dx, or just dx. And then we let a be equal to 3, because a squared would be 9. And so the antiderivative in this problem would be 1/3 arctangent of u over a, so that would be x minus 4 over 3 plus an arbitrary constant. Okay, now there are some problems that might have been hard before that now we can kind of piece some things together that we've been talking about. And the problem, if you're careful, the problem's not too bad of a problem. So let's say we have 2x plus 9 over x squared plus 64 dx. Now remember, don't forget the things we've already discussed as far as integration goes. And so in the last lecture, we did talk about the form du over u, right? And we've talked extensively about that form now, that's the natural log of the absolute value of u. And so, if you look at u in this problem as being x squared plus 64, well, du would be 2x dx. Unfortunately, in this problem, I don't have a 2x dx in the numerator. I have 2x plus 9 dx. So this is a problem where, if you're careful, this actually is an easy problem, but you have to be careful. And you have to know this trick that sometimes it's to your advantage to split the integral up into two integrals. So if I wrote this as 2x over x squared plus 64, that integral plus the integral of 9 over x squared plus 64, like so, now all of a sudden I can do this because this is going to be the form for the first term is going to be du over u. And if you want to formally write out the substitution, you can do that. Right? You can let u be x squared plus 64, then du is 2x dx. That's exactly what I have. And so you could actually make the substitution here and get du over u, which is the natural log of the absolute value of u. Now I'm not going to put a plus c here because I have another integral, and I'll end up adding the plus c in at the very end. All right, and then in this next problem, or the next integral, what would be happening here? Well, you're going to try to match this up with du over a squared plus u squared, like that. Right? And so what would we do here? We'd let u be, and now in this problem, technically, you'd want to use a different variable for the substitution, I guess. Technically you should do that. So I would maybe write this all in terms of v. But I'm just going to go ahead and leave this with u's here because I think it's pretty clear what's happening. So u is x, and then du would be dx, and a would be equal to 8. And if you look at those expressions and substitute them in, you would want to bring out the 9. Where the 9, the 9 has really nothing to do with matching this form up. So if you take the 9 outside of the integral, now this matches up exactly, right? And so this would be plus 9 times 1 over 8 arctangent of x over 8, u over a, plus c. And so our final antiderivative here, the first term would be the natural log of the absolute value of u, so the natural log of x squared plus 64, and then plus 9/8 arctangent of x over 8 plus c. So splitting the integral is a nice trick to know, and sometimes that's going to work really to your advantage to do that. So that's what I did in that problem. It's definitely something that's good to know. All right, so now let's move on to the arcsine and the arcsecant forms. Those are the other two that we need. And I'm not going to derive these forms. These are simply from the derivative forms. So remember that the derivative of the arcsine of u of x is equal to u prime over the square root of 1 minus u squared, right, using the chain rule. So turning this around and then making it a somewhat more general form like we did with the arctangent, you get this form, that du over the square root of a squared minus u squared. If that's our antiderivative that we're trying to write down, right, this would be equal to arcsine of u over a plus c. Now notice that what ends up happening is, and it's because of the radical and the algebra that happens because of the radical, is notice that the arcsine form does not have a 1 over a in front of it like the arctangent did. And then we also have the form, the derivative form for the arcsecant, excuse me, that the derivative of arcsecant of u of x would be equal to u prime over the absolute value of u times the square root of u squared minus a squared. All right, so if we turn this form around and write it out as a integral form, this would be du over u times the square root of u squared minus a squared, and that would be equal to 1 over a arcsecant of the absolute value of u over a plus c. So notice the arcsecant form does have a 1 over a in front. Now all we're doing is turning these derivative forms around, and there's a little bit that you have to do with the constants to prove those. So, all right, so let's look at some examples that kind of relate back to these forms. We're going to approach these exactly the same as we did the arctangent form. So next form, we have 2 over x times the square root of 9x squared minus 25. All right, so the first thing you'd want to do, if you're going to try to match this up, and if you're looking up at those forms, the arcsecant form seems to be the one that you're going to try to head for because of that x that's outside of the radical, and because notice the difference in the expression underneath the radical. For the arcsine, it's a constant minus the function squared, but for the arcsecant, it's the function squared minus the constant. So that order does matter because it's subtraction, and so you have to kind of pay attention to that also. And I did not write the dx down in this integral. I needed to do that too also, definitely. All right, so in our problem here, we want to identify the function that's being squared in the denominator. And so the function that's being squared in the denominator is 3x, and then minus 25, like that. So if I let a, well, let's not start with a, let's start with u like we've been doing. If I let u be 3x, then du would be 3 dx. So I need to do a little bit of work with that. And then a, well, I've got 25 there, so a would be 5. And this does almost match up with what we need here, right? We need a u and and du in the numerator there. So we've got a little bit of work to do here in that. First of all, I'm going to take that 2 outside the integral. So this is dx over, and then we have an x times the square root of 3x squared minus 25. Now notice that that's the u squared, that u is 3x. So I've got to have a u sitting outside the integral also. And so I need to multiply in the denominator there by 3 to give me a u on the outside of that radical. And since that 3 is in the denominator, then I need to multiply by 3 in the numerator in front of this integral like this. And then what else is going on here? Well, not only do I have those things going on to make that 3x match up with u in the denominator there in front of the radical, but du is 3 dx. So I need a 3 dx in the numerator, so I multiply by 3 there, and then that would give me a 3 in the denominator right there. And believe it or not, with all of that stuff going on, this is going to match up exactly now. If you go through and look at this, that 3 dx is du. The 3x outside the radical is u. And then underneath the radical, I'd have u squared minus 25. So this is perfect. It matches up exactly. So the 3's divide out, and I'm left with 2 times, and then this is simply an arcsecant form. So this would be 1 over a, so it would be 1 over 5 arcsecant of the absolute value of u, so this would be the absolute value of 3x, divided by 5, and then plus an arbitrary constant. And so then you end up with 2/5 times the arcsecant of the absolute value of 3x all over 5 plus a constant like that. And that would be our antiderivative. So you have to take your time on these problems, kind of watch the constants, make sure everything matches up exactly. It's got to match up exactly with the form that you're trying to achieve in the problem. All right, the next integral. This is a definite integral. We haven't seen one of these today. So we're going to be using the fundamental theorem to evaluate this. So you have the integral from 0 to the square root of 2 of 1 over the square root of 4 minus x squared dx. And again, remember, you might see this written as 1 over the integral from 0 to the square root of 2 of dx over the square root of 4 minus x squared. Now let's write down the arcsine form again here. We know that if you integrate du over the square root of a squared minus u squared, that this is simply arcsine of u over a. Let's see. So that's the form we're trying to head for here. All right, so this ends up not being too bad here. If we let u be x, because that's the function that's squared underneath that radical, then du would be dx. That's what I have in the numerator, so that's good. And then a would be 2, because we have the square root of 4 minus x squared. So a squared is 4, so a would be 2. So this matches up exactly with the arcsine form. So this is going to be arcsine of u over a, not plus a constant, because this is a definite integral. And this would be evaluated from 0 to the square root of 2, and it wouldn't be u over a. I'm not sure why I wrote that, because u would be x. So this would be x over 2. That's better. All right, so now you use the fundamental theorem to evaluate this, and you have arcsine of the square root of 2 over 2 plus the arcsine of 0. Now remember, the arcsine of the square root of 2 over 2, you're saying that the sine of what angle in either quadrant 1 or 4 has a sine that's equal to the square root of 2 over 2, right? And so that would be pi over 4 minus, and then the sine of what, it would be equal to 0, right? And this is again in quadrants 1 and 4. And that would be 0. So this is pi over 4 minus 0, or just pi over 4. And so that is the value of that definite integral. Okay, so we are doing good. Now let's look at a completing the square problem that is also an arcsine problem. So that presents a little bit of difficulties because of the radical and how that works out. So in this example, we have 2dx in the numerator over the square root of 4x minus x squared. So we have the square root of a quadratic expression in the denominator. Don't have a constant term, but I have an x term. And that x term is telling me that I'm probably going to have to complete the square to see if I can get this to match. All right, so don't forget the form. It's never a bad idea to be writing these forms down. But you have du over the square root of a squared minus u squared is arc sine of u over a plus c. Okay, so there's no way to make this match the form like it is because of that x term, and so we need to complete the square to see if we can get it to match the form. Now you have to be really careful with the arithmetic here. This is the way I write this out, and you're going to see different people write this out different ways. This is what I do. So as I take the square root of, and then I turn the terms around and put the x squared first. This is negative x squared plus 4x. I want the squared term first. And then I factor out whatever the coefficient of the x squared term is. And so I have to factor out a -1, and that leaves me with x squared minus 4x. I'm going to leave a space because I'm going to complete the square. And then I'm going to have to do something outside the radical also. All right, so what do you add in on the inside of the radical there? I'm going to go ahead and write this step down again. So this is -1 times x squared minus 4x. And half of 4 is 2. 2 squared is 4. So I'm adding in a 4 right here. That's plus 4. But then you have to decide what to do on the outside of the integral, outside of the parentheses there. And so you have to do the opposite of what you've just done right here. But this is really -1 times 4, or -4. And so outside the integral, I'm going to add 4. Remember, you have to do the opposite right there. So -1 times 4 is -4. So to do the opposite, I'm going to add 4. Which is good that you're adding 4 here, because now you can turn these terms around. And underneath the radical, I'll put the 4 first, and then minus, and then x squared minus 4x plus 4 factors is x minus 2 squared. The 2 in the numerator of that integral has really nothing to do with what's going on, so I could bring that outside. And sure enough, this is going to be an arc sine form, right? If I let u be x minus 2, that's the function that's squared. Then du would be dx. That's perfect. And then a would be 2. And sure enough, this is going to match up exactly. And so the 2 on the in front of the integral just comes down for the ride. And then this would be arc sine of u over a. So this would be x minus 2 over 2. And then plus an arbitrary constant like that. There's nothing I can do to cancel those 2's out. You can't multiply that 2 because it's not a multiplication problem. This is function notation. So we're just stuck with it, the antiderivative in that form. All right, so you've seen some good problems having to do with the inverse trig functions. And so lots of good examples here. And so now what I want to do is finish up the lecture today by talking about the hyperbolic functions a little bit. I'm not even going to assign any homework on the hyperbolic functions, but I do want to cover these. And hopefully you watch this. I'm doing this for those of you going into Cal 2, because in Cal 2 you've got to know something about the hyperbolic functions. Not a huge big deal, definitely not a huge big deal, but it's something that you need to at least be familiar with. All right, so we start off with some definitions right away here. We have the hyperbolic sine function, and the abbreviation for the hyperbolic sine is SINH of x. And the hyperbolic sine is defined to be e to the x minus e to the negative x over 2. 1x didn't come out real well, so let me change that. Okay, that looks better. That's the hyperbolic sine function. If you look at the graph of the hyperbolic sine function, just use those exponential functions to sketch the graph. What ends up happening is that the graph fits through, whoops, let me put that in a different color, goes through 0, 0, right? Because if you put in 0 in there for x, you get e to the 0 minus e to the 0, so that's 1 minus 1. And this graph actually kind of fits in. You have this function right here, which is the function e to the x over 2. And then you have this function right here, which ends up being, oh, I didn't exactly graph that right. Let me go back and back that up just a little bit. I apologize for that. This goes through 1/2 right here. So you have a function, an exponential graph that looks like that. That's our graph for e to the x over 2. And then negative e to the negative x over 2. What you're doing is splitting that fraction up, the definition there, and you get a graph that kind of looks like that. And that's the graph of the negative of e to the negative x over 2. And what ends up happening is the hyperbolic sine is kind of the combination, or is subtraction of those two. And what happens is that the hyperbolic sine just gets really close to those functions. And if you think through the arithmetic, you can see why that would be true, but that the hyperbolic sine kind of fits in between those, that those graphs actually fit in as asymptotes for the hyperbolic sine. And so this is the hyperbolic sine function right here. Okay, the hyperbolic cosine the abbreviation for the hyperbolic cosine is COSH of x, like that. And the definition for the hyperbolic cosine is e to the x plus e to the negative x over 2. And if you look at that graph, since this is an addition problem, it works out a little bit differently. You have the function e to the x over 2. Kind of missed it right there from 1/2. Try that again. Maybe a little bit better. So there's e to the x over 2 right there. And then e to the negative x over 2 is just the reflection of that graph around the y-axis. Kind of looks like that. And there's e to the negative x over 2. And the hyperbolic cosine is simply this, you're looking at the sum there. And so the graph fits in between them. Again, they act as asymptotes, and hyperbolic cosine kind of looks like this. It's really close to those two graphs, doesn't actually ever get there. So that's the hyperbolic cosine graph. Hyperbolic cosine graph sometimes is used to model, like when you have a bridge, or let's say you have, this is the ground right here, and you have telephone poles suspending cables, right? Or electrical lines between these poles. And what happens, the cables kind of drape along like this. And when you have those shapes, the hyperbolic cosine is frequently used to model that shape like that. All right, as far as calculus goes, the derivative, and if you think about the definitions, you can easily prove that this is true. The derivative of the hyperbolic sine function is the hyperbolic cosine function. And the derivative of the hyperbolic cosine function is the hyperbolic sine function. They kind of sort of mimic the properties for the trig functions, but not exactly. There's some differences, and you can see here that the hyperbolic cosine's derivative is the positive hyperbolic sine, whereas if there's just the cosine function, we know that the derivative of the cosine is negative sine. All right, and so if you've got those derivative forms, then you get the integral forms, the corresponding integral forms follow along, that the antiderivative for hyperbolic sine is hyperbolic cosine, and the antiderivative for hyperbolic cosine is hyperbolic sine. And then, you know, you've got some other things going on in that the hyperbolic tangent function is simply the hyperbolic sine divided by the hyperbolic cosine. You know, and so you could write that if you wanted to as e to the x minus e to the negative x over 2 over e to the x plus e to the negative x over 2. The 2's divide out, and then the hyperbolic tangent function looks like this, as an exponential function, like so. The derivative of the hyperbolic tangent kind of mimics, again, the trig functions is the square of the hyperbolic secant. You know, and the hyperbolic secant is 1 over the hyperbolic cosine. Hyperbolic cosecant is 1 over the hyperbolic sine, and so on. All right, so I'm going to write etc. here because, you know, I just wanted to briefly show you some things about the hyperbolic trig functions. You know, so you shouldn't panic then if you see something like this as an antiderivative, right? The antiderivative for the hyperbolic cosine of 3x would simply be, well, the antiderivative for hyperbolic cosine of x is just hyperbolic sine of x, so that 3 just means you end up with a 1/3 as a constant in front of the hyperbolic sine. And there's your antiderivative right there. Right, 1/3 hyperbolic sine of 3x. And the same thing with the hyperbolic sine. Hyperbolic sine of pi x dx, that would simply be 1 over pi hyperbolic cosine of pi x plus c. All right, now as far as the exam goes, the exam 3 does not cover the material that we covered today. Exam 3 stops at exponential and log functions and integration. So if we quickly look back at the review, I'm just going to flip back here and look at the review for exam 3 right here. Right? Exam 3 then starts off with some optimization problems. And in this case, you know, I've given you a couple of optimization problems, a box problem where you're cutting out corners, a problem where you're fencing something along the side of a building or along the side of a river, and then a problem where you're inscribing a rectangle inside of a figure. I'm going to tell you right now that on this exam, I'm going to ask you 2 questions, and they're going to be similar to these problems that I have on this review. I've got 3 problems on here, and I'm going to give you 2 problems on the test, and they're going to match up with these 2 of these 3 problems. Okay, not exactly the same problem, but they're going to be very, 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 very similar. So be watching for that. And then we're going to moving on to area. And on problems 4 and 5 here, I ask you to draw pictures with left hand and right hand endpoints. And so I'm going to ask you to do that. And it should be a really quick problem. Not much to do there at all, to draw out a picture to show what using right hand or left hand endpoints would do as far as a picture, as far as the rectangles go underneath the curve. Problem 6 is a Riemann sum problem, and that's the kind of problem where, again, I'm going to ask you that problem as a take-home problem. Problem 7 on the review is evaluating some definite integrals where the region that you're talking about is a regular geometric figure. In this problem, I've got a triangle and a trapezoid and a semicircle as the three shapes there. So be expecting something like that on the test. On these problems, 8, 9, 10, and 11, we're simply looking at relating area under a curve or between a curve and the x-axis or between two curves and integrals. And so it's just asking you to write the integral that describes those pictures. And then we're going to move on to antiderivatives and indefinite integrals, some pretty basic problems, and then some that'll be a little bit more difficult. Some definite integrals where you have to use the fundamental theorem, and that finishes up through 26, and then we're looking at u substitution problems, and there'll be a few u substitution problems, and I've given you lots of examples here to look at for u substitution problems, including some problems that we did talk about in lecture where you have to use long division. I give you 2 examples like that. And then finally the test finishes, and by the way, notice also that exponential and logarithm functions, the exponential function figures in some of these problems, and the form du over u, which is a logarithm, fits in on these problems. So exponential and logarithm functions will figure in to these integrals. And then we finish with the second part, or actually the first part of the fundamental theorem of calculus. That should be a very easy problem. That's number 41 there. And then a couple of limits at infinity to deal with. And then after that, I've got all the solutions to the problems worked out. Now the review mimics the test very closely. The test you'll find is pretty close to these. The test is pretty close for sure to this review. It will not be as long as this review. So I've given you lots of problems to practice here. So please be working on these as you prepare for exam 3. So please come by my online office if you have any questions. I have had some students in calculus coming by on a relatively regular basis in the evening, and that's a great thing. I'm glad you're doing that. You just come by and ask questions. That's awesome. I remember I have on-campus hours this week, so don't forget my on-campus hours on Wednesday and Thursday. Good luck preparing for exam 3 as we head on into this last regular exam of the semester. Remember, we will have one last lecture next Wednesday to finish up the semester. And that'll be a relatively short lecture on area between two curves. It's not going to go as long as what maybe some of these lectures have gone. So have a great day. Let me know how I can help. Thank you.